Hello and welcome again to our specialized lecture course on quantum gravity. So we have 12 lectures and today is the third one. The first two were devoted to a general motivation of why we are interested in developing a quantum theory of gravity which does not exist in a final form, in in an accepted form by the community. And also gave a brief overview of the kind of approaches. Now, today and also the next lecture course is devoted to one approach. In fact, the oldest approach, where you just take Einstein's theory of general relativity and you apply quantization rules as you do in fact successfully for say electrodynamics. Now you have classical electrodynamics, then you turn classical fields into operators and so on, and you find a consistent theory of quantum electrodynamics that is also empirically tested and maybe the one of the best tested of all theories. If you think about say the G-2 experiments at accelerators. So this is what is also tried here, starting with the first paper by Rosenfeld in 1930. And covariant means that in the formalism you do not spoil the four-dimensional covariance of Einstein's theory. We shall see later that there are also other methods called canonical or Hamiltonian methods where you split this up into P's and Q's, and so this is equivalent to this approach, but the covariance is not explicitly seen. Now here covariant means that really the covariance is never spoiled at any part in the formalism. Now today I will discuss the central concept of a graviton, which is very important for the covariant approach, and next time I will give at least a brief overview of path integral approaches, which are the modern approaches of this. Now, the graviton, as I will write down later, is a massless spin 2 particle and is believed to be the mediator of the quantum gravitational field in an analogy to the photon, which is the mediator of the electromagnetic field. The photon is also massless and has spin 1. Now, the starting point here, and this is where the concept appears, are actually weak gravitational waves. Starting point, weak gravitational waves. As we discussed in the lecture course Relativity 1. So if you want to see the details of that, please go back to the videos of Relativity 1 or consult your favorite textbook of that. It's a standard. That's the formalism of the linearized Einstein equations and then the polarization states of the gravitational field and so on. Yeah, so what we do is making the ansatz that the four-dimensional metric G mu nu can be written as a sum of two terms. The first is a background, which is here taken to be the Minkowski background. So we assume that space-time and we are still at the classical level here. Space-time is approximately flat, yeah, and we use coordinates, inertial coordinates, and Cartesian coordinates, where this here has the form diagonal -1, 1, 1, 1. So the Minkowski metric. So this is fixed, and the dynamics is in small perturbations. And small means that whenever you do calculations, terms higher than linear are neglected. So f mu nu times f mu nu is neglected, or also when derivatives appear, we also assume that f mu nu comma rho and so on times f mu nu comma is also small. Now whatever, independent of derivatives or not, is higher than linear will be neglected. And this is important. No? So I cannot overemphasize this. So important is here the presence of a background. As I will emphasize later in my lecture courses, that quantum gravity, and I said it in the introduction that quantum gravity, the essential thing is the background independence. But here at that level we start, because that's anyway how we are used to construct quantum field theory. We are on Minkowski space and have some fields, and so if you make this ansatz, then you can try to do it an analogy to quantum electrodynamics. So now the Einstein equations then. Well, I should say in the GR course I call this 2 psi mu nu. It's just to be in accordance with the terminology here that I don't have the 2 here. So don't be confused if you go back to the other lecture course. You can get all the expressions then by just having f being 2 psi. Then you're on the old terminology. Now, so the Einstein equations then with this ansatz. Okay, and I neglect the cosmological constant here, it's not important here, lead to then an equation for this. And of course it's a linear equation because you only have linear terms, and it's a wave equation because the Einstein equations are second order, so what else should you get than a wave equation? So D'Alembert f mu nu is minus 16 pi g, and you have t mu nu minus 1/2 eta mu nu times t, and t is the trace, the trace of the energy momentum tensor, which is formed by here with respect to the inverse of the Minkowski metric. So whenever the t appears, it's not time or whatever, it's this trace. And also from now on, in most expressions, I set speed of light equal 1 because that's the standard. So we measure space-time just in meters, not in meters and second. So speed of light equal 1. So that's the central classical equation. We're still at the classical level here. That's what we have. Now I should also say that to arrive at this, a certain condition was used for f, because we have this coordinate independence of the theory, and at the linearized level we also call it gauge independence, and so we can fix a gauge or the coordinate system to simplify it. And here the so-called harmonic condition was used. Harmonic condition, which is f mu nu is so f mu nu comma nu, so it's the four-dimensional divergence of f mu nu is not 0 but 1/2 the trace of f comma mu. So that's the analog of the Lorenz condition in electrodynamics, where you have the four-dimensional divergence of a mu is 0. But here you have two indices, so this is why this term appears. Okay, so because of this gauge freedom or coordinate freedom, right? If you transform x mu to x mu plus some epsilon, then also the f mu nu transforms. So under x mu to x mu plus epsilon mu, with terms epsilon squared, which are all the, whatever is here with indices is equal to 0, or just write it like that. Yeah, we have f mu nu goes to f mu nu minus d mu e mu minus e mu minus d mu e epsilon nu. So the generalization of what you had in electrodynamics for the gauge transformation, where you have a mu goes to a mu plus d mu epsilon. That's what you have, and here we have of course some functions, epsilon with 4 functions. Right. I should also say here that this can be further simplified by redefining f. Then this term here with the trace can be absorbed in the definition. So if we have f mu nu bar is defined as f mu nu minus 1/2 eta mu nu f rho rho, then we get from the linearized Einstein equations an equation for f bar and it's just minus 16 pi g times t mu nu. Now that's also what we did in relativity 1, and that's, I mean, the simplest you can write down. It's just the standard structure of an inhomogeneous wave equation. The D'Alembert of the field is just directly given by the source. No? So again in electrodynamics you have here this equation for A mu, and you have here the source, which is here the current, the electromagnetic force current. Okay, the harmonic condition then just reads d mu f bar mu nu equals 0, and is then in full analogy to the Lorenz condition, d mu a mu. Now, so you see there's a one-to-one translation of concepts from linearized gravity to electrodynamics, which without sources is linear. And from here you find the usual solution. A method of Green function, you have then the retarded solutions, the retarded waves, and so on. And what I want to emphasize here is that here this condition, right, if you apply to the left-hand side, you get 0. You get also here on the right-hand side vanishing divergence. But it's the ordinary divergence, not the covariant one. And this is a feature of the linear theory. No? For the full Einstein equations, you have the covariant derivative. No? So this here is consistent with t mu nu comma nu equals 0, but not with t mu nu semicolon equals 0. Now, this means that in the linearized approximation, there's no energy exchanged between the gravitational field and matter. Of course, gravitational fields carry energy. This comes from the source, and this is in a sense from beyond the linear level. But then it's just carried with it, and there's no further exchange between matter and gravity here. No? So you see here, this is the standard divergence, and not the covariant one. Okay, let us have a look at the vacuum, at the free propagation, because this is what we need. So this is just setting t mu nu equals 0. And then of course you have D'Alembert of f bar is 0, but then also D'Alembert of f is 0. So D'Alembert of f mu nu is 0. And the simplest solution of this are plane waves. Of course you can then superpose the plane waves, but the simplest solutions are plane waves. No? And so you can write them down in the form f mu nu is e mu nu times e to the I kx plus e mu nu star e to the minus I kx. And this e mu nu is the polarization tensor. Well, that's the complex conjugate. Now, from this here, from D'Alembert f mu nu equals 0, then you get here that k mu is equals 0, and from the harmonic gauge here you get that k nu e mu nu is 1/2 k mu e nu nu. Now, as you also perhaps remember from the relativity class, is that the harmonic condition does not fix the coordinates completely. Now you have a remaining freedom, so you can stay within the harmonic condition and still have some further restriction. This restriction was to the so-called TT gauge, or transverse traceless gauge. So, we have this transformation here above. Right, and if you do that here, then you can have then, okay, we call that f mu nu prime, the transformed one, gauge transformed or coordinate transformed, and you can then check that if you transform the harmonic condition, which is here, f mu nu prime comma nu is f mu nu comma nu minus well, I should maybe shortcut this, so you can do this as a simple exercise. This minus 1/2 f prime nu comma mu is f nu comma nu minus 1/2 f nu comma mu minus D'Alembert of this epsilon mu. No? So that's the original harmonic gauge, which is 0, but we want to stay within that, so we demand this also to be 0, right? And you see that for this to hold, then this here must be 0. So if we do a coordinate transformation of that type and want to stay within the harmonic gauge, then D'Alembert epsilon mu is 0, or must be 0. And of course, this is a free wave equation like this one. So you also have plane wave solutions. No? So there's no contradiction to having plane wave solutions, because here this gives a similar solution, right? So you have here epsilon mu, I mean also plane wave solutions. And so we have epsilon mu of x is, for example, 2, the real part of I f mu e to the I kx, no? Where f mu is real. And okay, these are 4 functions. So all in all, you then get the following counting of degrees of freedom. So the 4 metric, which is g mu nu, has 10 degrees of freedom. And so by the harmonic condition, yeah, you can subtract 4. And then by the choice of these epsilons, then you remain 2. No? And so you cannot simplify this further, and this is why we call 2 the number of independent degrees of freedom of the gravitational field, at least in the linearized limit. No? So number of independent degrees of freedom for the linearized gravitational field. Yeah. So in chapter 4 we will discuss, the full nonlinear case, and there is some issue there about the counting of degrees of freedom in the full theory. But here in the linearized theory, there's no ambiguity. You have 2, and this will then be the degrees of freedom of the graviton. Will be. So So with this transformed f, you can of course have then a similar solution. So you have f mu nu prime is e mu nu prime e to the I kx plus e mu nu prime star e to the minus I kx. And this transformed polarization tensors, they are related to the original one by plus k mu f nu plus k nu f nu, with this f. You can easily calculate this, and I recommend you to do these calculations. They are straightforward to get some exercise with these quantities. Now, as in the relativity class, of course, we can use with profit one particular choice of the epsilon, which corresponds to the TT gauge. Which means transversal traceless. So traceless is that you choose the polarization tensor to be traceless, and also orthogonal to the direction of propagation. So here in the 4-dimensional sense. Now that's the first T. Well, the first is actually transversal, and the second is traceless. Is that? Now, so the waves, the linearized gravitational waves, they are transversal, as are the electromagnetic waves. And I don't repeat what I discussed in the relativity class. If you have, say, propagation in x direction, x1 direction, then you can discuss, the two linear polarization state, the so-called plus and the cross polarization, with the corresponding polarization tensors. And of course, you can superpose them, the plus and the cross, to find the circular polarized states, which I called ER and EL. ER, the right circular polarized, and EL, the left circular polarized. And then you can calculate the behavior with respect to rotation of these circular polarized wave with respect to an angle. So if you have here the propagation, and if you have here, then make a rotation against counterclockwise with an angle theta, then these circular polarized states have a simple transformation. Let me write it down. We had this in the relativity class. There were also exercises devoted to that. So the circular polarized states. So we had then the right circular polarized. If you make this mathematical rotation with angle theta, then you get here e to the minus 2I theta. So that's a nice calculation. You have to use the rotation matrix to do that. And the left is e to the 2I theta times EL. No? So these are the two. Okay, so you see, if you make this rotation under theta, they transform with respect to 2 theta. And that's, of course, a feature of the tensor nature of this field. Now, by the vectors, you just have the same theta, and here you have theta and 2 theta, which means that the ellipses that you have here of the linear polarization state, and if you know this kind of behavior, they are invariant with under 180 degrees with respect to the direction, not just 360 degrees, already 180 degrees. That number here in general has a name. It's called helicity. So if a wave transforms as a so general wave psi going to e to the I and a number theta phi, then H is called helicity. Now we are still in the classical theory, so not yet the spin. It's called helicity now, from the Greek word helix, something like spiral, and which means that the left circular polarized wave has helicity H equals 2, and this one has H equal minus 2. No? And quite generally, we can show that polarization axes of these waves, they are inclined with respect to each other by 90 degrees over H. So if H is 1 as an electromagnetism, they are just orthogonal to it. And here you have 45 degrees, if you remember from the plus and cross polarization. If you have fermions, then helicity would mean spin 1/2. Then you have, instead of 360 degrees, 720 degrees, which are this double-valued feature of fermions. But that's not what we are interested here. Okay, and just to mention it again, for the electromagnetic waves, of course, you have helicity +1 and -1, and you have vector fields. So H equal 1 for electromagnetism, or ±1, I should say, depending on left and right for electromagnetic wave. Okay. Now, we have this weak gravitational waves F mu nu, and of course, say also as a part of the starting point for the quantization, one would like, of course, to have, say, a Lagrangian or an action for F mu nu, like we have a Lagrangian or action for the electromagnetic field. And this, of course, one can derive straightforwardly, of course, with calculations. You have to put that ansatz into the Einstein-Hilbert action, and neglect all higher order terms, except then in the action, of course, you need quadratic terms, which give then rise to linear terms at that level. And this was done by Fierz and Pauli. So the field equations for linearized gravity follow from the Lagrangian, the Lagrangian density, and this is derived by Fierz and Pauli in 1939, and it's also called the Fierz-Pauli action. Let me write it down. You don't have, of course, to remember this. It has these kinetic terms which are quadratic, but because we have these many index combinations, you have various terms, and then you have the coupling to T mu nu. So just let me write it down. So L Fierz-Pauli is 1/64 pi times the gravitational constant, and then you have here terms that look like that. You see typical kinetic terms which are quadratic in derivatives. Like already in mechanics, you have 1/2 q dot squared or m q dot squared minus f mu nu comma sigma f sigma mu comma nu minus f mu nu comma nu f rho rho comma nu plus 2 f rho nu comma nu f sigma sigma comma rho, and then you have the coupling to T mu nu, which has this form plus 1/2 T mu nu f mu nu, and so it's a standard exercise then for the classes to take this and to check the field equations, right? To use Euler-Lagrange equation in general, and to check that from this you find this. After use is made of the harmonic condition, of course. Otherwise, you get many more terms. So from this you get Euler-Lagrange equations and harmonic condition. Then you get, D'Alembert f mu nu is minus 16 pi g T mu nu minus 1/2 eta mu nu. So why do we do that? We are happy in principle with this, and of course in relativity usually we only work with this and we don't need that. But as you will see the course of that lecture series of lecture, that we like to start with Lagrangian action when going to the quantum theory. For example, the path integral, you sum over different configuration with e to the I action, as you see. This is why we are interested in having this, even if it looks now a bit complicated. So if we have this without that term, then of course we get the Lagrange function for free f mu nu field in Minkowski spacetime. So LP FP without 1/2 T mu nu f mu nu term. So you have L for a free f mu nu field in Minkowski space. And if you have that, then in principle you can then calculate by the standard expressions a canonical energy momentum tensor for the gravitational field itself. Okay, in general we don't have an energy momentum tensor for the gravitational field, but here just having this as or imagining this as a standard field in Minkowski spacetime, we can use the standard expression from the Noether theorem and get and calculate an energy momentum tensor. No? So calculate from this, I mean from the one without that term, the canonical energy momentum tensor for the linearized gravitational field itself. So let's see what comes out of that. Okay, it's usually called small t mu nu, and must not be confused, of course, with the standard capital T mu nu from the Einstein equations, which is on non-gravitational matter and fields, not gravity. Now, so let us call this. And the formula from Noether's theorem is that you get dl over df alpha beta comma mu f alpha beta comma mu minus eta mu nu l. Okay, if you calculate this, then you get a long expression, as you can imagine from this, and this is I leave as an exercise, but it's greatly simplified by going to the TT gauge. No? So go to TT gauge, or I should say, I think I'm happy with just the harmonic condition, and that's simply enough. So use harmonic condition to find. Okay, let me proceed here, and also after averaging over space-time region, so it's not really a local quantity at a certain point x. There's still an ambiguity for that. I mean, depends. I mean, because of the equivalence principle, you cannot localize energy. But if you average over space-time regions that are much bigger than omega to the -1, I mean the frequency that is here, I mean, which is omega is equal k times c, because then terms like e to the -2i omega t minus x, they just cancel out, and you don't have them here in the expression. So you get here the expression t mu nu, and this means averaged. So the averaging is here that, which is k mu over 16 by g, and then you have e alpha beta star, e alpha beta minus 1/2 absolute value of e alpha squared. No? And one can show that this is invariant under transformation of this polarization tensor that correspond to these coordinate transformations here. No, that's invariant under e mu nu going to e mu nu plus k mu f nu plus k mu f nu. Okay, so that's the expression that one gets here in the linearized theory. And so you can attribute an energy momentum tensor to the linearized gravitational field, so it carries energy even if there's no then exchange of energy with matter. Okay, then you could, in people in field theory, so maybe more coming from the Richard Feynman point of view, not the Einstein point of view, one to start, I mean, with field theoretic concepts. You could start with this as your fundamental Lagrangian for tensor field. No? Like you have the electromagnetic Lagrangian for a vector field in flat space. No? And that could give you a theory of gravity, and what would that theory of gravity then look like? No? So L Fp as a fundamental Lagrangian for a gravitational tensor field in flat space time. That would be certainly a point of view very different from Einstein's point of view, where you just have Riemannian space, and here it's field theorists who are only trained, say, in quantum electrodynamics or classical electrodynamics. They would say, okay, now let's take that as our theory. Of course, there's then the problem that T mu nu is not covariantly conserved, as I wrote down here. Here this is only, you only have the usual divergence here, and not that. So there's no exchange of matter. So you have to, of course, implement that, because otherwise the theory is wrong from the very beginning. No. So the problem is we have T mu nu comma nu equals 0 instead of T mu nu semicolon nu equals 0. So we try, at the level of the field equation, so to have D'Alembert F mu nu bar. So the D'Alembert F mu nu bar is this equation, which is of course consistent with that. Is minus 16 pi g, and then you have T mu nu. Then you just add, why not, the energy momentum tensor of the linearized field by hand, which is this one here. So then would we have the source is from matter and from gravity by hand, right? So but this here is quadratic in the fields. Well, this is of course the polarization tensor, so this is the field. It's quadratic in the field. So to get this from the Lagrangian, you would have to modify this and add a cubic term. So this is T mu nu is quadratic in F mu nu. So need cubic term in L. But if you have a cubic term in L, then of course you must consider this here to get a modification of this, right? So so this modifies T mu nu, and then you would have to add this again here, right? Add this modified this in the equation, and so on. Then you have a whole infinite process, right, of having here another term, having to modify this, getting again another term, having to modify this. So the question is whether this iterative process can be summed up. And that's actually what Stanley Dazer, in a very nice paper, investigated. It's already from 1970. So he actually showed that this infinite summation by a very clever redefinitions can be done in one step first, and that it turns out that the eta mu nu, which is here, the background, is unobservable, and that the metric the matter, couples only to the sum, that only the sum is relevant, and that the resulting action by this process is the Einstein-Hilbert action. So even if you were totally ignorant about Einstein's theory and you only knew about the field theory in flat space-time, and you would have been interested to have this Lagrangian as a starting point for a gravity theory in flat space-time, for reasons of consistency, you find that only this combination here enters, and that you get an action that, if you know what the Riemann what a Ricci scalar is, you can write in terms of the Ricci scalar. Of course, if you don't know, then it's explicitly written in terms of the G mu nu. So DESA, in 1990 show, I mean, infinite summation can be done actually in one step. And it turns out that matter couples to G mu nu is eta mu nu plus F mu nu, and that the resulting action is the Einstein-Hilbert action. Yeah? So if you consult the thick book by Misnosan and Wheeler, I mean the thick black book, they have I think 6 or so paths to Einstein's equations, how you derive them in different ways. One of them, these different routes, is this route here by DESA, that the field theoretic route, that you start with a thing in flat space and want to make it consistent, and actually you find Einstein's theory and the Einstein-Hilbert action. So if history had been different, if Einstein had not been around and so on, and people just had discussed maybe other fields and would then have tried to develop a gravitational theory from this, then they would have arrived at Einstein's theory from a very different route. DESA in 1970 showed that actually eta mu nu is unobservable, and you find the Einstein-Hilbert action from this field theoretic point of view. And if you have it, of course, you know that this is a geometric theory, and that the equivalence principle follows then from that, instead that you derive at the equivalence principle. Well, I mean, we started from a candidate for gravitational theory with helicity 2, I mean this tensor field. Perhaps you say, why doing that? If we go just to field theory, why not having other simpler fields? No? Okay, I just mentioned this reference by Straumann. So other helicities for gravity, question mark, and you can have this nice review by Straumann that you find on the archive at Astro PH. So it's some time ago 000. If you just write this number, then you get it. So the point is, there are other helicities, for example fermions. Yeah, do you want to describe the gravitational field by fermions? Well, one can show that this is inconsistent. Also, I mean, you find these arguments in Feynman's book. Feynman has also a book, Lectures on Gravity. Well, other people have edited this after Feynman's death, but it's a nice book. So that this is not possible because spin 1/2 particles, they change the intrinsic state of the objects, and you get no static interaction. I mean, you don't find Newton's limit here. So that's not possible. Okay, you have maybe a vector theory. Yeah, I mean, electrodynamics was very successful. So why not do a gravitational theory with vector fields? In fact, this is what Maxwell already had tried and saw that it's not possible. You know? Because you get, in gravity you only have masses that are positive. No? So if you consider, in electromagnetism you have positive and negative charges. In gravity you only have positive charges, which are the masses, if you like, but they attract each other in positive, whereas positive electric charges repel. So and this is why you cannot construct, directly an electrodynamic type of theory of gravity. No? So this is also a no, because you have repulsion for positive charges. in vector theories. And so this here would correspond to the masses. Now, and of course that's, yeah, I mean I would not be attracted here, but I would somehow fly away, and that's not what we observe, right? So but that was already known to Maxwell. Now, Maxwell was very clever, and of course he wanted to also construct a gravitational theory along the lines of Maxwell's equation. And then he saw, oh no, that's not that simple, and let's see. I mean, it was only much later with Einstein, and it was much more complicated. Okay, but then scalars remain, right? Scalar theory. Which is simpler than Maxwell's theory, and you can say, okay, we only have positive charges, not positive or negative, so maybe a scalar field is sufficient. And this is actually what was tried before Einstein completed relativity. And the most famous one, I think it was also the first one, is the one by Nordström, Gunnar Nordström. And it's known as the Nordström theory of 1913. And he had suggested the following Lagrangian L is minus 1/2 eta mu nu d mu phi d nu phi minus 4 pi g times t. So that's the trace of the energy momentum tensor times phi. So of course, if you couple to phi, you cannot have indices here, and you perform the trace of that. That's the simplest. Plus the matter, that's L matter. No? So phi is the gravitational field. Yeah. And instead of the metric. No? So just in Newton's theory, we also have one phi, and why not just doing generalizing this to special relativity? And then you get the field equations. Check yourself that you get the field equation where phi is 4 pi g times t. No? So you just have here the trace on the right hand side. But what turns out is that the physical metric, I mean, if you discuss in this theory, I mean, the propagation of masses, I mean, clocks and rods and the like, they only react to a metric which is not eta mu nu, but eta mu nu multiplied by phi squared. So the physical metric as measured by rods and clocks, rods and clocks is g mu nu. That, okay, must be defined from this, and it's phi squared times eta mu nu. No? So again, you see this eta mu nu is somehow not really important. It's not observable even in this theory, right? You have to multiply this with phi squared. Now, then motivated by this, Einstein and Fokker in 1914 presented a different formulation, actually already a geometric formulation, because Einstein at the time was already familiar with Riemannian geometry. And Fokker, by the way, is a Dutch physicist that you perhaps also know from the Fokker-Planck equation of statistical mechanics. So they had a different formulation of Nordström's theory, formulated with the Ricci scalar, and so the Ricci scalar is 24 times g times t. No? So this was before the Einstein equations. No? So you see, in the Einstein equations, of course, you also have something geometric here, and you have here some t mu nu. So this is the Einstein-Fokker equation. But of course, I mean, Einstein-Fokker immediately thought that this is falsified by observations, no? Because there is so this is a contradiction to observations. So there's no light deflection, for example. because the trace of the electromagnetic energy momentum tensor is 0. So in this theory you don't get an interaction of electromagnetism with gravity. And Einstein, of course it was before the light deflection was directly observed, but Einstein in 1911 already concluded from the equivalence principle there should be a light deflection. And also, I mean, this was of course Einstein's main issue, I mean, to check that the perihelion motion of Mercury comes out right. Of course, you have here perihelion motion, but this is really clearly different from what you observe. Yeah, so wrong prediction for perihelion motion of Mercury and of course of other planets. Also, I mean, from a more aesthetic or mathematical point of view, this theory has an absolute element. I mean, this you can already see here, which is the conformal structure. I mean, of course, only the G nu enters, not the eta mu nu, but the G mu nu has the simple form of phi squared times eta mu nu. No? So this means that if you think in terms of geometry, the space-time here is conformally flat. And so this is a very special space-time and not what Einstein already at that time had in mind as a general space-time. No? Okay, also say absolute element namely the conformal structure. Space-time is conformally flat. Okay, so in principle, I mean, a scalar theory would be fine, so that does not seem to be, I mean, in contrast to this mathematical problems, but the theory, still is a little bit, special here from the geometric point, and of course it's wrong empirically. So every physicist would just cross this out. So, and this is why only tensor fields remain. And so that's when Einstein found in 1915. And what we also get from a different point of view using the Fierz-Pauli Lagrange Desers method. This does not mean that scalar fields are not used in gravitational theory. So they're often used, but as additional degrees of freedom for the gravitational sector. So if you go beyond Einstein and have some candidates for generalized gravitational theory, then people, for example, have take a gravitational sector, the G mu nu, and one or even many scalar fields. We have no time here in that lecture course to discuss quantum versions of these, but this is, you find in the literature, it's called so-called scalar tensor theories. So today we only have scalar tensor theories as generalizations of Einstein's theory, which we do not discuss here. For example, they also come as so-called effective theories, approximate theories from something like string theory. You can derive effectively, say, a gravitational sector with metric plus scalar. It's often called a dilaton in string theory. So that's just a side remark. But we are happy with the simplest and most conservative, which is just the Einstein theory, just the metric, no scalar field. In the gravitational sector, of course, there may be scalar fields in the matter sector, like the Higgs field, and quantize it. Okay, so far for the classical theory. Now, of course, we are interested in the quantization, and if you first adopt, say, a purely quantum mechanical point of view, we then go to field theory. Then what one usually does is one translate the helicity of this mediator field into what is called spin. So quantum mechanics of the gravitational field. So it is the one particle sector. So we translate I mean, this is our heuristic recipe into spin. But that's what you have in electromagnetism. You have helicity plus minus 1, and okay, the absolute value of this is then the spin, which is spin 1 of the photon. And because gravity is long range, so as electromagnetism, so this particle with spin 2 should be massless. So long range interaction. And this is why we propose a massless spin 2 particle called the graviton. Now the name, I don't know who actually first that's his name. It was first coined in the 1930s, I mean by the pioneers, so Bronstein and others. Also Heisenberg and Pauli thought about it, and in these circles, I mean, this name emerged at some point. So we have to ask the historians who first, in a written form, have suggested graviton. I have no time to do this here, but just mention there is in the literature so-called Van Damme-Feldman discontinuity that is a strong argument for the massless nature of the graviton, and this is different from electromagnetism because if you have even a very, very small mass, then you get a measurably different light deflection. So this argument points in favor of really exactly massless, although there maybe are some theoretical ways out, but at least in a straightforward way you have this. Now in the quantum mechanics of this, then if you talk about particles are usually defined or classified, if you like, by the Poincare group of the background. That's what Eugene Wigner in 1939 came up with, and for which also other things he got a Nobel Prize in the 1960s, is that particles, I mean particles is just the name, I mean you should not imagine this as small spherical things that children play with, but okay, particles are classified by irreducible representations of the Poincare group. And he showed that one can classify them by two parameters called mass and spin. So mass and spin. And so once you fix this, then you can do all the mathematics connected with this. And so this you can find in many textbooks. I mean, in my book on quantum gravity, it's summarized in other textbooks such as Weinberg's textbooks. So that's, I mean, a kind of standard discussion, and I will not repeat it here. I mean, you can find it in so many places. You start with the Poincare transformation and look for, of course you have to learn some group theory and discuss the representations of this. And of course you have to distinguish between vanishing mass and non-vanishing mass. So for vanishing mass, always only 2 degrees of freedom remain. But for non-vanishing mass, it depends on the spin. You have 2 times spin plus 1 degrees of freedom. And from this you can also then find, I mean, that this massless spin 2 particle has that properties that we associate with the gravitational field. I mean, correspond to this helicity eigenstate of the circularized polarized wave. Okay, that's something. I mean, if you like to study this, you can read in the literature, or you can just take it for granted here. Of course, today, I mean, we have in our universe, the background actually is not Minkowski space. So in cosmology, we have the cosmological constant, and asymptotically goes to the zeta space. So you might study representations of the zeta group. That's also something that one can do, but that will not actually affect these results. Okay, and that's theory, so you would expect an exactly massless spin 2 particle. Observations, of course, is something different, and you find restrictions in the literature from I mean, different types of measurements or arguments. So one is that the mass of the graviton mg must be smaller than around 7.7 times 10 to the minus 23 electron volts. So that's from the detection of the gravitational waves, from the LIGO and Virgo collaborations 2017, because you can measure, I mean, the speed of the gravitational waves in a sense that come from these sources to here, and of course if this is not speed of light, then it would correspond to a non-vanishing mass, but that's what they give. And there are also other references where you can have even better limits from pulsars, and so that's not important to discuss now the exact numbers. It's just to point out that from observations you get these very strong constraints, even stronger than for the photon. I mean, from observations you get that the photon is restricted by the order of 10 to the minus 18 electron volts. So the photon is massless at that order, which is, you see, at least 5 orders of magnitude worse than this limit. Now, if you calculate the Compton wavelengths corresponding to this number, then you find the Compton wavelength is bigger than 1 light year. So this, even if it has that limiting mass, I mean, its wavelength that is I mean, huge. It's astronomical. So, but at the moment we believe that graviton is massless, and there's no reason to doubt that. Okay, that is for the quantum mechanics, but of course we deal with fields, and gravity classically is a field, so we have actually to develop a field theory of quantum gravity. And because I discussed here linearized gravity, of course it's our task now at the end of today to discuss the quantization of a linearized field theory. So quantization of a linearized field theory. So we had at the beginning today, we had as classical solutions the plane wave solutions. F mu nu is e mu nu e to the ikx plus e mu nu star e to the minus ikx. Now in quantum field theory, we address the superpositions of these, and transform the amplitudes into operators. That's what you do when you quantize in field theory. You don't have a position operator or something like that. You turn the classical amplitudes of the field amplitudes, into operators. So so in field theory, then you have, I mean, the superpositions of plane wave solutions, and transformation of amplitudes into operators. So let me do that here on that second blackboard for clarity. So we have then here f mu nu of x. Okay, then you have we sum over the two our spin or helicities +2 and -2. I mean, this is called here sigma plus and -2. I mean, the spin is 2, but depending on whether you have parallel or antiparallel to the direction of propagation, you have +2 or -2 as the spin component. And then we integrate over all k. So whoever of you has ever heard a lecture course on standard quantum field theory, of course, has encountered free fields at the beginning and knows what I mean here. Yeah. But even if you haven't, just let me mention again, you take the plane wave solution, you superpose them, and you turn amplitudes into operators. This is by definition the quantum field. Okay, that the measure is like that. One can justify it because of Lorenz invariance. I mean, in standard textbooks you just have d4x, but then you can rewrite it, and you have this spatial momentum here, absolute value. Yeah, and then we have here the amplitudes. Here the polarization, e to the ikx plus a dagger of k sigma e to the mu star of k and sigma e to the minus ik. No? And so these a and a dagger originally were the classical amplitudes, and they have now become operators. So that's the Hermitian conjugate. And because these are free fields in a sense, you do it as you quantize the harmonic oscillator. So they are, in a sense, old friends from quantum mechanics, namely the creation and annihilation operators. No? So A, respectively, a dagger. So they are the annihilation, respectively, creation operator for a graviton with momentum h bar k and helicity sigma, and they of course obey the standard commutation rules. I mean, a of k and sigma does not commute with a dagger, but there is a delta on the delta sigma sigma prime, the Kronecker delta, and the delta function here. No? That's, I mean, the generalization of the a dagger equal 1 in quantum mechanics. So that's what is meant by quantization. So to get this here. And historically, it was first done by the pioneer Bronstein that I already mentioned in the first chapter in 1936, who really wrote down first this quantization of the linearized field theory. Now this f mu nu that I had earlier, or this f mu nu here, and is also an operator, but cannot be, although it looks like an ordinary Lorenz tensor, but it cannot be a tensor under Lorenz transformation. Why? Because we don't want to have helicities other than +2 and -2. But the TT gauge where you get this is not Lorenz covariant. So if you just make a Lorenz transformation of this, then you jump outside the TT gauge and you get other helicities. But that's not what we want and what we don't think is consistent. So if you go to another Lorenz system, you have a Lorenz transformation, but you must compensate this by a gauge transformation to go back to the TT gauge. No? So f mu nu under Lorenz transformations, under Lorenz transformation that I denote here by this matrix, is then the standard form for if it were a Lorenz tensor, lambda mu rho F lambda rho, but you must compensate this by a gauge transformation minus d mu epsilon mu minus d mu epsilon no. So additional gauge transformation, yeah, to stay within the TT gauge, no? And to preserve this interpretation of helicity, helicity plus 2 and minus 2. And okay, if you see the coupling, or inspect again the coupling in the Fierz-Pauli Lagrangian, now you have this 1/2 F mu nu T mu nu, and you see, okay, if you have this invariance under this combined transformation, so in particular under this, if this term appears, it must couple to a conserved T mu nu, because you have this partial derivative that you can partially integrate to here, and this additional term of course should not contribute, otherwise you would have explicit gauge terms, no? So you have to couple it to a conserved, so this must obey, I mean, T mu nu comma nu, I mean without not a semicolon, because the linearized here, because of that here. So otherwise you would not have a gauge invariant coupling, and something analogous holds for electrodynamics. In electrodynamics, I mean, the vector potential also is not a vector under Lorenz transformation, but it transforms like that. Also has in addition this gauge transformation. So I mean, in the Lagrangian there you have this coupling A mu times J mu times the current, and again because of this, and it should not enter here, so this should be invariant, and if you make a partial integration it means that the electromagnetic current must be conserved, so you get d mu J mu 0. Now, so you see that gauge invariance and conservation law, I mean, come together. Okay, at the end I want to sketch here a nice argument by Steven Weinberg from the year 1964, and it's also, okay, it's summarized in my book, but it's also in more detail presented in Weinberg's textbooks on quantum field theory in the volume 1, if you like. He said that if you start, or he showed that if you have spin 2 theory where you start with, and a theory that is Lorenz invariant of spin 2, then you can actually derive the equivalence principle. And from this, okay, you can argue that you can find general relativity as Einstein did. And what he considered was, I mean, a general scattering process. So, okay, so you have some ingoing particles, and it's not specified, and some outgoing particles. For example, from the standard models, I mean, they have some interaction, and okay, the ingoings I label with alpha, and the outgoings I label with beta, just the name. And then on top of this, he considers the emission of a graviton, a so-called soft graviton. Soft graviton emitted. This is a graviton with arbitrary small wave numbers, so arbitrary large wavelengths, k going to 0. And so, okay, if you have then here, this particle has then for momentum p plus k. If this has momentum k, then okay, this here has then p, no, for my momentum conservation. And then he considers the amplitude for the emission of a soft graviton. Okay, maybe I can just do it here. So amplitude, no, which he has beta alpha just stands here now. I use Weinberg's notation for ingoing and outgoing particles, and then you have the usual tensor indices, and it depends on k, and so it's written as the product of the amplitude without that times, the times what you learn in quantum field theory, how this is described in terms of Feynman diagrams. Now I understand that not every one of you has already learned how to deal with Feynman diagrams, so I just give this here. Those who have seen Feynman diagrams before, they know what I mean. Those who have not seen, maybe you just believe me that this is the result. Right? So that's the amplitude without the graviton emission, and then you have the sum over n. So these are about the in and outgoing particles, and then you have this term. I tell you what this means: eta n, gn, pn mu, p n mu over p n mu k mu minus I eta n epsilon. Okay, what are these terms? I mean, the eta is here either +1 for outgoing or -1 for ingoing particles. I mean, here we have 2 ingoing and 4 outgoing, but this can be general, right? And you have some numbers here, -1. So that's the eta. So the Gn here is the coupling of the graviton to particle n. So of course the coupling can be different to any type of particle. We shall then Weinberg then prove that it's the same to all particles, but here it can be different. No? Maybe to the Higgs it's different than to an electron, whatever. And okay, these are then the momenta here of the particles, of the in and outgoing particles, right? So if we consider the emission of a graviton with a definite helicity, let me just continue here. So emission of graviton with a definite helicity. No, so if one calculates then this matrix element m beta alpha mu nu on k, and or project it on the corresponding polarization tensor. E mu nu, I mean, corresponding to helicity +2 or -2. And we know that this transforms under Lorenz transformations. Transforms under Lorenz transformations as, this is what we had here. With this term, I mean, the f mu nu is written as e mu nu times e to the I kx. So here, as e mu nu goes to lambda mu lambda mu rho e lambda rho plus k nu f mu plus k mu f mu. I mean, this we had before in the solution of this. And a Lorenz invariant result is of course then achieved only if k mu times this vanishes, because otherwise you have these gauge terms in it. No? So Lorenz invariance means that k mu times m mu nu beta alpha of k is 0. Now if you do that, I mean, I should have said, okay, this is just for the regularization. This perhaps you know already from elementary quantum field theory, when you have the propagators, that you shift this a bit away to the imaginary part, and you take epsilon to 0. So anyway, this is just for the mathematics, and will then be 0. So if I multiply this with k mu, then you see I have here Pn mu times k mu, and this is cancelled out with that here. So I find from this then that we have the sum over n, eta n, gn, Pn nu is 0. Okay, then recall the definition of the eta n. So they are +1 for the outgoing and -1 for the ingoing. So I can have, I mean, the +1s on the left-hand side and the -1s to the right-hand side. So it means that the sum of all sum of n, gn, Pn is conserved. Yeah, because you have this the -1s you just put here. Yeah, but for non-trivial processes here, I mean, the only known, I mean, conserved quantity is the total momentum, actually. No, but only total momentum sigma sum over nPn is conserved, and this means that all the Gn must be equal. So all Gn must be equal, and you can set it to some number. Okay, if you can also consider the units, the physical unit it had, we can set it as follows: Gn as the square root of 8 pi g. Of course, this is the correct thing, I mean, to get back, I mean, the linearized Einstein equations at the end. So that means that all low energy particles, I call it graviton, here this low energy with spin 2 and mass 0, they must couple universally to all forms of energy, and this is what we call the equivalence principle. Now, of course, in disclosing. So this means all low energy particles with spin 2 and mass equal to 0 couple universally to all forms of energy, and so this is what we call the equivalence principle. Of course, now in this language here of particles, and this is what we know leads to general relativity. And Weinberg shows also by this type of arguments you can, for example, exclude spin 3 and also higher spin as candidates. Now, I did not discuss them here. I mean, I discussed here possibility scalars, famous vectors, and of course spin 2. But you may ask, why not spin 3 or spin 71 or whatever? But they look into Weinberg's book. They can not be candidates for the gravitational field, because actually one can show that they have no couplings that exist actually in that limit, and so they have no Newtonian limit, no 1 over r squared force. So you can just forget about them. I mean, you get Newtonian limit, the 1 over r squared, force of Newton from the spin 2, and actually Bronstein has already shown that you can find back from spin 2 the Newtonian gravitational force. Yeah, this type of arguments are also relevant if you, for example, discuss string theory and the like, and spins and string theory, but this is not our purpose here. Just to mention, I mean, if you do, you can apply the same arguments for electrodynamics and have a photon here, which is spin 1, and k equals 0, and what you then find is, I mean, for quantum electrodynamics, the analog of this would be that the sum over all n eta n of the various charges to which the photon couples is 0. So you get just charge conservation from this argument here. That's also what Weinberg in the 1960s had written many very nice long technical papers on quantum field theory. I mean, even before the Standard Model and all that. But they are very general, and they really deserve to be not forgotten completely. Okay, so far for this first half of the covariant quantization. So next time I present, of course, a similar brief review of the modern point of view of covariant quantization, which is basically path integrals and what we get from path integrals. Thank you for today. Until next time.